during the training phase. And yes, we need to see how model works there. So yeah, we can see that quality is a bit worse, right? So our predicted versus actual points are distributed a bit another, right? So sometimes we have higher errors, and we can analyze the predicted versus actual plots in time. So this is for our training period. We already seen this plot, and this one is for the first week of production usage. And yeah, we can see that model still follows the trends, but sometimes, for example, right here, let's see what is happening, or maybe go even closer. We can see that in peak moment, our model tends a bit underestimate the demand, right? So we are almost always a bit lower than the actual value. So maybe it's the trend, maybe not. Let's continue our analysis. So again, we can move to the year distribution. I especially like this plot because it helps to see whether we tend to underestimate or overestimate the demand. And that's how it looks like. The peak year is still around 0, but there is small like movement to the left part, right? So you can see that we pretty often start to underestimate the demand. But okay, I'm just analyzing the time and suggest us to move faster. So let's just ignore the rest part of the dashboard. If you're intrigued, spend some time to analyze what we have there, because there are a lot of plots. And I'm going to move to the second week to see what we have there. So let's just move here. So we can continue analyze the model performance in order to see what is happening with the model. But one more important thing is the target drift or concept drift. We need to figure out whether maybe the world has changed, and this is why our errors start increasing. So let's do this. Let's create a dashboard, which is called target drift dashboard. In this case, we generate dashboard object again, but here our tab will be not regression performance, but numerical target drift tab. And let's calculate the target drift first for first week. So we did it, and let's see how it looks like. Again, we are using method show. If you want an HTML file, we can use method save. So our target drift is not detected, which means that our target function, at least during the first week of production, looks pretty much the same. And we can see that the distribution is more or less looks similar, right? So we can see how our target correlates with the features. We can see how it looks like during the time. So probably during the first week, there is no target drift. The model year is comparably bigger than during the target and the training period, but still normal. So maybe we can continue using this model. And of course, no prediction drift here. So let's move further. We have our second week, and I suggest us move directly to third week. So let's see what will happen after 3 weeks of production usage of our model. So let's start from the regression performance. Here we use the same reference, but we take third week of production usage. Let's calculate it. And let's see how the dashboard looks like. So now it's third week of production usage. So we have our model in production approximately for a month. So a lot of time has passed. Now our mean absolute error is 29 bikes. So it's much bigger than during the training phase, right? So the percentage error is higher, and mean error without the absolute function is pretty high. So let's see how the plots looks like. Yeah, here it is. And let's analyze the actual versus predicted in time. Now we clearly can see that our model tends to underestimate the demand. We can see it because our red line is almost always behind the gray one, and you can see it especially during the peak moment. When we have higher demand, we always tend to underestimate it. When we have lower demand, it looks more or less okay. So probably something is happening during the peak moments. So let's continue analyzing what is happening. We can see there that, well, we definitely almost always underestimate the demand because our year is almost always under the green line, under the 0, right? So this is the trend. And let's see the distribution. And the distribution now even doesn't look like normal because it's really shifted to the negative part. So we underestimate the demand a lot. So now we understand what is happening, and we need to get some hypothesis on why actually it happens, right? So what has happened with the world, or maybe our model, or what? So let's see the rest part of our report, which is called underperformance segments. So we can split our objects into 3 groups. The major group, the top 5% objects where we tend to underestimate our demand, and the top 5% of objects where we tend to underestimate our demand. And let's see whether this error on this object somehow connected to the features, because, well, if we tend to underestimate the demand for objects with the specific feature value of some features, then probably there is some connections between these features and the error. So let's analyze that. And for doing this, you have the error bias table, where we calculate the error and the feature values there in order to make some conclusions of what has happening. And we sort this table based on the connection between the error and the feature values. And the first feature here is attempt, which feels like temperature. So let's open it. And this is the distribution which we see there. So we have the distribution of feature values for a segment of majority objects, for a segment where we tend to underestimate the demand, and for a segment where we tend to underestimate the demand. So you can, for example, switch off the majority and compare our estimation and underestimation distributions between reference and current data. So during the reference, we tend to underestimate and overestimate the demand during the whole region of temperatures. So there is no clear connection between the temperature and model error. So it's evenly distributed, more or less. But when it comes to the 3rd week, which is our current data, we can see that we tend to overestimate the demand during the lower temperatures and tend to really underestimate the demand during the higher temperature. So our first hypothesis can be that the temperature really influences the model's error. So probably our model didn't really learn some patterns related to the temperature. But we can continue this analysis and see that the second important feature here is temperature, which is really, again, super connected to the previous one. And I will again switch off the majority because we just do not need it now. And we can again see that we tend to underestimate the demand during the higher temperatures and overestimated during the lower ones. So maybe we can already create the hypothesis that probably it was the bad idea to train model over the winter period and then apply it over the spring one, because, well, now we experience the better weather. Probably people start to use bikes more often, and our model just didn't learn this pattern. Of course, this is more like an example, but this is something that can happen with production model, where we do not consider some connections between the features and target, and maybe seeing something like this. But yeah, with help of such tables, we can analyze the reasons. And let's see whether we had any chances to maybe earlier catch things like this. For doing this, we could use data drift. So let's assume that we started to use data drift from the very beginning. For example, we calculated our data drift not like during the 3rd week, but during the 1st week. So right after we trained the model. So let's do that. I will simplify the column mapping a bit because I'm interested only in data drift for numerical features, just because we saw that the most important features that actually cause the error are related to temperature, wind speed, and that's all numerical features. So let's quickly create dashboard with data drift tab and calculate the data drift. So now we can see the data drift interactive table, which contains the information about 6 numerical features. And here I can see that 4 out of our 6 features are drifted, right? So the data drift is detected for pretty a lot of features. And we can see here that even during the 1st week of production usage, we can see that our temperature, feels like temperature, humidity, and wind speed has shifted. So distributions are different. And of course, no drift for weekday and hour, but that's logical enough, right? We do not expect such features drifted anyway. So we can analyze the distributions and the feature values, right? And we can see that, well, our current data has shifted a bit to right. So the temperature tends to be increased comparing to the training period of time, right? So if you know in advance, and we should know this, that temperature and feels like temperature are important feature for our model, then if we see the data drift for these features, we can already start preparing and expect some model quality degradation coming next, right? So this is why I believe that data drift is a very nice proxy for model performance monitoring, right? And we can often use data drift earlier than performance, right? Because for calculating data drift, we do not need any ground truth or our target function. As soon as we have features, we can calculate data drift. And this is why we believe that data drift is a very nice proxy. As soon as you have input data, you can analyze it. And if you have some hints or information about important features, you can start like preparing to future model degradation if you see some data drift. So this is all I wanted to share with you today. I hope it makes sense and maybe help you to inspire you create some comprehensive or vice versa, more simple monitoring schema, and make sure that your production models works exactly as you expected during the training phase.
Thank you very much, Emeli. Yeah, of course, it was very, very interesting. I think that and more than 1,600 people start your GitHub repository, so that's massive. And yeah, we have just a couple of minutes, guys, for quick questions, because unfortunately there was lots to discuss in this session. So I will start fishing questions in the chat. Daniel is asking, what kind of test are you using here? Kolmogorov, Smirnov, or something like this?
Yeah, great question. Didn't mention that, but yes, for data drift analysis, we use different tests. It depends on the feature type. And for now, for numerical features, we have only Kolmogorov, Smirnov, but we're adding soon Anderson one, just in order to improve the quality. And for categorical features, we have Z-score best test for binary categorical features, and Chi-square for multinomial categorical features.
Okay, thank you for the answer. Is there any other question that I want to ask, that you would like to ask Emeli now? Because we are really tight on time here. If not, I would really like to thank you, Emeli, for the amazing session that you provided us with the code and everything. That was hell of a work. And thank you all for attending this session. I will just post here in the chat a reminder for registering for the datalift summit in June, where we will have lots of use case in production. And thank you all for attending this datalift number 6, and see you around. Thank you all for attending.
Thank you everybody for attending.
Bye-bye.
Hope to see you next session. Bye.